All right. So we're gonna kind of take this unit slow. What am I thinking? Tomorrow's Friday already, right? Yeah. So I plan on getting you the take-home test tomorrow. I will then post the video to the take-home test on Monday, because then whatever you do on the take-home test, you can use on the actual test that we'll have on Tuesday. Does that make sense? Yeah. But let's take a look at this. This is some real applications. So on page 178 or 171, worksheet number 15, it talks about you have this entrance to a store. You have this entrance to the store that makes a parabolic archway. Okay, so let's think about what this might be. Like if you had, let's say this is the store. This is fancy dancy store. It says the door to go in is a parabola. Okay? That's all they're talking about right now. Can you kind of envision what that would look like? I mean, just, it's not a square or rectangle door like that. It's actually curved. Okay? It's a fancy place. Okay? So they tell us that we have this equation, and they're using something called H at T. H at T is just a fancy way of writing y. It's a height equation. So this right here, this is the same as y. Okay? So we're going to build upon that with this. So let's think about this equation. This is a parabola. Okay? So we kind of know that it's going to look something like this. This is our door. 171. All right. You still with me on this adventure? So we have this curved shaped door. That's all really it is. All right. So let's think about a couple things that we could generate off of this. First thing I want to do is I want to do this. So I made it 0. What that's going to find is going to find us this point and this point. Okay? So this is the ground. In this case, the ground is the x-axis. Okay? And I'm sure we're going to have the y-axis that's going to do this. Y-axis. And this is like the height in feet. Okay? All right. So we need to try and think about how we might solve this problem. And we've learned all these techniques on solving. We've learned the quadratic formula. We've learned factoring, setting things equal to 0 so we could solve it traditionally. So how would we maybe just break that down? Any thoughts? I mean, it's out of order, but that's okay. Any ideas? Like, what do I have in common between the two that are underlined? I do have an x. Very good. Thank you. So right now, if I factor an x out, I'm going to get 12 minus x. So I've just factored out the x from the traditional thing. And if we go and solve this, that means I know that x is equal to 0. And then 12 minus x equals 0. Solve this. So subtract 12. And multiply both sides by -1. So what this gives us, this yields us the point 0, 0, which is right here. And this gives me the point 12, 0 right here. And let me just pause there. So does everyone understand that we're trying to figure out the size of this doorway? Okay? It's a parabola door. I'm not quite sure who makes their doors into parabolas, but let's just pretend it's some weird store that's like, oh, let's have everything mathematical functions as all of our decor. I don't know how popular that place would be, but let's just pretend. Okay, does everyone feel comfortable so far with what we have done? Okay, we okay? And again, notice I didn't like make things real fancy. I just kind of tried to say, hey, we have some information here. We have this door that happens to look like a parabola. It is what it is. Let's see. What did we call this very, very, very top thing? What would that be called as far as a parabola? Starts with a V, ends with an X. Vertex. So this is our vertex. So the vertex is where a parabola either goes from going up to going down or going down to going up. It's either the highest point if it's an opening down parabola, or it's the lowest point if it's an opening up parabola. All right, so how far would you think this would be right here? So let's answer this. How wide is door at bottom? What do you think? Do I know how wide things are? Do I know 2 points? Did I find 2 points? What's one of the points I found? 0, 0. And what's the other point? 12, 0. From 0 to 12 is how big? Huh? I heard it, I thought. Yep. How far is it from 0 to 12? 12. Okay. So the door is 12 feet at the bottom. Okay, so let me just highlight where this is on our graph. So we have 12 feet from the bottom. So from this distance to this, that yellow distance right there on our little diagram is 12 feet. Now, I have a question. Do you think, so from this point here to this point here is 12 feet. What about from like this point here to this point here? Is that still going to be 12 feet? Or is it going to be closer? Closer. And as I move up, if I get way up here, is that closer? Is that 12 feet or is it less than 12 feet? So this is the widest my door is going to be. And as I go up the door, the distance between my fingers is getting closer and closer and closer. It's getting less and less and less than 12. Agree? Until I get exactly to the vertex, then the distance from my vertex is 0. There's not a distance. Okay? All right, so let's see if we can figure this out a little bit further. So if the distance between the doors is 12, what is halfway in between 0 and 12? So 6 is kind of called probably our axis of symmetry. So this point here is 6, 0 right here. Okay? That's where our axis of symmetry lives. Remember, the axis of symmetry includes the vertex. So my axis of symmetry is x equals 6. Okay, so my friends, how do I find the rest of the vertex? If I know the first number has to be 6, how do I find the rest of the vertex? How do I find the rest of the vertex if I know? What do you think? Plug it in. Yeah. I'm going to plug the 6 in here and the 6 in here. So I'm going to get 12 times 6 minus 6 squared. What is 6 squared? 36. And what's 12 times 6? 72. 72. So 72 minus 36. So it's 36. So my vertex is at 36. So my door, the door's highest point from the ground is 36 feet tall. Oh my gosh. We have a door that is 12 wide at the very bottom, and it's 36 feet tall. I mean, the ceiling in here is like 10 feet. So it's like more than 3 of these ceilings. That is a big old door. Oh, I like Willy Wonka. Good stuff. Huh. So we're just kind of like maneuvering our way through this. So our store happened to get this box. You have this big old box that's delivered, and this box is 8 feet wide and it's 22 feet tall. And they want to know, hey, can I take this big box, 8 foot wide? Okay? For me to you is 8 feet, roughly. Might not be exactly close. And it's how tall? 22 feet tall? So more than 2 of these ceilings tall? Dude, we got a big box of something. I hope it's full of candy if it's Willy Wonka's joint. I like it.
I feel like the Renaissance Festival has doors like this. Like legitimately. Like,
they could.
Thinking about it. Because they used to have doors like this.
So what we want to know is, could I push this 8 foot by 22 foot tall box? Could I push it through our door? Okay, so I'm going to go to another screen. I'm going to kind of draw what we know. I'm going to draw what we know. Okay, so we have this parabola. This is our door. And down here at the very bottom, it is 12 wide. Is that right? And how tall was it? How much? 30. What's my vertex? 636? So it's this tall, 36 tall. So this is 36 tall. And these are in feet. Okay? So now we wanted to know, how big is my box?
8 feet wide.
8 feet wide and how much tall?
22. Oh.
Okay, then it's 22 tall. So this could fit. Okay, so we're trying to push that box through that doorway. All right, so now let's use a little thought process. Do you think I would probably push this box right through the middle of the door, or do you think I'd have it pushed over to one of the sides? Like, you ever driven on I-25 and on a couple of the bridges there over by Spear and I-25, it'll say caution, lowest height this. So if you're in the lane that's closest to the middle of the road or the lane that's closest to the edge of the road, that's where the bridge is lowest because the bridge is kind of an arc to it. Okay, so the middle lane is the tallest. So you want to push it through the middle. All right, let's figure this out. Okay, so we're looking at this 8 feet wide. So if it's 8 feet wide, I'm putting the center of the box right here. So how far does it go this way? And how far does it go this way if we're putting it right through the middle? So this is 4 feet this way and 4 feet this way. You still with me? Does everyone understand where I got the 4 feet from? Okay. So the big question is, if I get to that, is this box going to fit through this doorway? And I don't know. It might be taller. I don't know. All right, so let's think about this. I know that I had this labeled on my original as 0, 0. And I know I had this labeled on my original graph as 12, 0. And then this point right here is at the point 6, 0. Okay? So at 6, 0, or at 6, 36, was that it? That was our vertex. So now we have to know, is this distance right here and this distance right here, is it less than 22 tall? So my original function was this. H at t is equal to 12x minus x squared. Okay? Okay, so we're using a little logic. Because let's face it, we like to work smarter if we're moving stuff, not harder. Like you ever Family ever have you try and move a sofa upstairs? And your stairs switch like 3 directions on the way up? What's something that kind of happens? It either fits or it doesn't. Or mom's getting all upset because you're scuffing up the wall because you're trying to make more room than there really is. Okay, so my friends, what is this point right here? What do you think? Based on what we know. Two comma 0. So let's and then this one should be 10 comma 0. All right, now let's think about how we got to that. Okay. If this is exactly at 6, if I count left 4, because it was 4 this way, I go 5, 4, 3, 2. If I count up from 6, I go 4. If I count 4 up, because it's 4 width, this goes 7, 8, 9, 10. Okay? So width-wise down here at the bottom all day long. So this is going to be the point 2 comma something, and this is going to be the point 10 comma something, and our comma something is the exact same. The height's going to be the exact same because we pushed it right through the middle. Now, my friends, I could plug 10 in or I could plug 2 in. It doesn't matter which one you plug in. It's going to give me the same height. So where do you think I should plug the 2 or the 10 in and figure out the height? Yeah, I'm going to plug. So what do you want, 2 or 10? 2. Okay. I'm going to take the 2. I'm going to plug it in here and here. So my h at 2 is going to be 12 times 2 minus 2 squared. 12 times 2 this week is 24. 2 squared is 4. My friends, is our 8-foot wide and 22-foot tall box going to fit through this door? No. I got to somehow figure out 2 feet because the width of that box is going to be 8 feet, and we're going to push it right through the center of the door. Yeah, our door is really tall at 36 feet, but the ding-dong designers of our store made it a parabola, not a rectangle. This isn't going to fit. Our box is too tall. So box is too tall. We're not pushing this box through. We got to figure out a different way to get it in. Okay? But do you think companies might take into account if they're having a really big piece of machinery put through a door? Do you think maybe they would take the dimensions into account before they actually ordered it to make sure they could actually get it inside? Well, I tell you what. Let's say you ordered this piece of machinery. Let's say this is a $100,000 piece of machinery that you need inside your store or your company. You're now going to waste an awful lot of time, money, and expenses because the dimensions what this came in doesn't fit through your door.
Or, for example, a really good one. This summer, I got myself a beautiful blue velvet couch.
Velvet?
Okay? Oh, it's so pretty. So pretty. But American Furniture, I asked them to deliver it because there's no way I can carry a couch up 3 flights of stairs in my apartment. They had to ask me, hey, is the width of your hallway big enough for 2 people and a couch? Okay, because I live in an apartment. I'm on the 3rd floor, and is your couch gonna fit through the door? So like it actually like moving companies or like for example if you get furniture at American Furniture or somewhere where they deliver it, they actually you do have to measure it just to make sure. My hallways are really wide in like going up to my apartment, so that wasn't the issue. The issue was actually trying to get into the apartment with the door. So we had to figure out, because what happened is you have apartment here, apartment here, apartment here, apartment here. And so I'm this corner. And so, but then when you open my door, my kitchen is right there. My countertop is right there. So they had to figure out, okay, we're going to have to push it up. And then when they could swing it around, because it's not enough width-wise between the 2 apartments, then they had to make sure they didn't hit my countertop. and then they had to push it down, pull it that way. Then I had to close the door, and then they had to rearrange it. So it's a lot of like, not like mathematical like this, but it's a lot of like figuring out, okay, is this gonna really work? Like, can you get it in? And it did, and it's beautiful. It's a beautiful couch. I love it.
All I know is if I was an owner of a company and one of my employees ordered something that we had to have and they didn't check to make sure we could get it inside, I think me as the owner of the company are going to be a little bit upset going, dude, this won't fit. That just wasted time and wasted money, wasted effort. So,
and
I mean,
if my door wasn't big enough, American Furniture wouldn't have actually delivered it.
Yeah.
They would have asked me to pick a different place.
Oh my gosh, jeez.
Because they don't want to bring their workers in and to deliver it
And then,
if it's not going to be an easy, like, plop and go.
Wow. Good for them for forward thinking that. I bet you in the beginning with American Furniture, they probably got to a point going, I am sick and tired of our guys taking something out and then having to bring it back on the same truck. It didn't fit.
And it's because delivery is extra cost.
Uh-huh.
So you have to be, especially on the weekends.
Yeah.
So it's Saturday and Sunday. So if it doesn't, if you still get charged, if you.
All right. Problem number 2 on that page 171. Problem number 2. You have somebody who is going to make themselves a garden. Someone's going to try and make a garden. Okay? They happen to buy this brick that would account for 20 feet. So as I go all the way around my garden, I guess it's not that big of a garden, but the whole distance around is 20 feet. Okay? So let's figure this out. So we have a rectangle, or it might be a square, I don't know. All right, so we have a perimeter of 20. That was told to us. All right, the length of the rectangle is x, and the width is 10 minus x. Now, I purposely went kind of backwards. Length and width, please take this out of your vocabulary. This was your elementary school teacher talking. They probably always said, oh, length is always longer than width. No, it isn't. It doesn't matter. Okay? Okay? It was just something that the elementary school teacher was like, oh, yeah, length is always longer than width. No, it isn't. So, with that known, would you agree that this top should be x and this right side should be 10 minus x as well?
Yes.
Okay? So, if you think about it, my perimeter equation is x plus 10 minus x plus 10 minus x, which equals 20. This is my perimeter as an equation. And if you worked it out, the x's cancel out and you get 10 plus 10, which is 20. Ta-da! Yay. All right. So in order to find the area of the garden is length times width. So we have x times 10 minus x. Okay? We want to find the dimensions because I could have 1 foot by 1 foot and 9 foot by 9 foot. I could have 2 foot by 2 foot and 8 foot by 8 foot. I could have 3 foot by 3 foot. And I just lost my count in my head. And 7 by 7. So I could have all of these different dimensions of my garden. So, huh? I could do 4 by 4, but that leaves me 4 feet of my perimeter of brick. Because 4 and 4 is 16, and I got 20 feet. I got 4 more feet I got to go.
Oh, wow.
Cool. All right. So my friends, we could multiply this out. But we're not going to. And the reason I'm not going to is this. If I set this equal to 0, and I set this equal to 0, I'm going to wind up getting this, which is this. Okay? So this if I had graphed it, is a parabola. Okay? Which means right now, my parabola kind of fits from 0, 0 to 10, 0. And basically, because if I multiply x times negative x, I get an upside down parabola. So if I find my vertex, the x of my vertex is going to tell me basically my x value is going around. My y value of my vertex is going to give me my maximum amount of area. All right, so my friends, I think we can do this. What is halfway between 0 and 10? What's halfway between 0 and 10? 5. So that right there is 5, 0. So I know that part of my vertex is 5 comma something. How do I find the rest of it? How do I find the rest of my vertex? There you go. So we're going to plug 5 in for x. So I get 5 and then 10 minus x, or 10 minus 5, which is 5 times 5, which is 25. So x is equal to 5. So what do you notice about my rectangular garden if all the sides are 5? My rectangular garden is a special kind of rectangle called a? Bless you. Bless you again. If all 4 of my sides of a rectangle are the exact same size, what's that rectangle called? It's called a square. So we have a square garden. A square is a special kind of rectangle. So my sides have to be 5 feet because 5 plus 5 plus 5 plus 5 is 20. Right? 5 plus 5 is 10, plus 5 is 15, plus 5 is 20. And my area is 25 square feet. Okay, now we just kind of played around with this a little bit. Okay? All I want you to do between today and tomorrow is I want you to give me an honest try for page 172. I want you to try and do 3 and 4. Now, before you look at it and you come rolling out to me or Miss Stone saying, I don't get this, read it. Talk to your neighbor. You know what? Ask 3 people before you ask us how they might go through the problem. I bet you might be able to hammer through it.